Hello everyone. So, what we are discussing is the measurement of fiber fineness. So, in last class we have discussed that the fiber fineness, fiber diameter measurement by microscopic method. So, where it is basically we have mentioned that it is applicable for only circular fiber, where the cross section is circular in nature, and after proper conditioning we have to put the fiber, we have to mix the fiber with the mount, okay, and then we have to mix properly, carefully it is mixed, and mount is selected in such a fashion that it should not swell the fiber, and the refractive index of the mounting agent should be different from the fiber, and typically liquid paraffin is used, and the mixture of fiber and mount is spread properly on the slide and covered with the cover glass, and slide is moved in zigzag fashion, so that to cover most of the fibers randomly. So, this is the way the slides need to be moved. Next method is that by air flow method. Air flow method, here we measure the fiber fineness indirectly, it is total indirect method, and here we do not measure the fiber fineness of individual fiber, it is a overall fiber fineness. Here we cannot measure the dispersion, that is the variation of fiber fineness within the particular mass. Okay. So, what we get? We get a overall fiber fineness of mass. Okay. It is basically it is a very fast technique, it is suitable for mill practice due to its speed of measurement. So, we get the rough idea of fiber fineness, fiber mass per unit area, unit length, or even its diameter, we can get rough idea. So, basically air flow rate at a given pressure difference through a uniformly distributed mass of fiber is determined by the total surface area. Now, let us see the analogy here we can make. Suppose it is a flowing river, okay, flowing river. So, this is the water is moving here, water is flowing. Okay. As water is flowing, if we see carefully at the bank of the river, the water actually flows in different fashion. Here there will be some different type of movement will be there, but from in the center, from other side it flows uniformly. This movement here, it is due to the drag of the surface. So, drag of the bank of the river. Okay. That means, for any fluid flow, when fluid flows through the surface, it flows through the any solid surface, that solid surface actually creates a drag here. Okay. This drag force, the drag force is proportional to the area through which the fluid is moving. Okay. Now, with similar analogy, if we see the this is a fiber mass. Okay. This is a fiber mass. Okay. Now, if we have say an arrangement of fiber mass, so this is the suppose here air is coming in and it is a outlet of air, and such two such arrangement we are making. This is another arrangement. here we are having say large number of large diameter fibers, and here we are having smaller diameter fiber. So, smaller diameter fiber, as we know, will have higher surface area for same mass. So, mass of the fiber in these two boxes are same, but smaller. So, this is A, this one is B, but specific surface area, that means total surface area per unit mass is higher in case of B. Now, if we see the if we flow the air at same pressure difference in both A and B. So, as B has got higher area of drag, it will result lower flow rate. Flow rate will be lower in B than flow rate of A. So, that is how we measure here. We measure here the flow rate for same pressure drop. So, indirectly we measure the specific surface area, and we are not actually measuring the specific surface area. We are telling this A has got higher surface area than B, okay, and that way we cannot tell the exact specific surface area, but from the large number of pre-calibrated data, we can calibrate the machine, calibrate the instrument, and from there we can tell okay, this is the actual value. So, using this basic principle, this airflow instrument works. Okay. Here in that instrument, here we can have constant pressure drop and we can measure the air flow rate, or else we can do in the other way also. We can have same air flow, but then we can measure the difference in pressure drop. So, in these two ways it works. So, air flow rate at a given pressure difference through a uniformly distributed mass of fibers is determined by the total surface area of fiber. So, that is actually proportional here. For a constant mass of fiber, that is actual volume. So, total mass is proportional to the volume, because for a same density. So, for a constant mass of fiber, the air flow is inversely proportional to the specific surface area, that we have seen already. So, air flow is inversely proportional to the specific surface area, means the total surface area per unit mass or per unit volume. So, that is the specific surface area here. It is the total surface area, considering the fiber is a circular one for calculation purpose. So, that is the total surface area, that is pi d is the perimeter of the fiber, and it is the multiplied by length, total length of the fiber. So, this is the total surface area and divided by the total volume, pi d square by 4 multiplied by L. So, this is the total volume of fiber. So, that means it is inversely proportional to the diameter of fiber. Okay. So, diameter of fiber. So, that means if we see the air flow rate is inversely proportional to the diameter of fiber. So, that is the air flow rate will be directly proportional to the diameter of fiber. That means, higher the diameter, the air flow rate will be high. So, in that way, if we can calibrate a machine, calibrate the instrument, we can directly get the diameter. Okay. So, air flow is directly proportional to the diameter. Now, the principle here is that the specimen is actually packed here, it is a fiber chamber. In the fiber chamber, specimen is packed Now, with the air suction arrangement, the air is sucked. Okay. Now, air flow is with the pump, using pump, air is actually sucked, and then the air is flowing and creating certain air pressure, for a certain air pressure. So, this air flow rate we can measure. The fiber sample of specific mass we have placed here. So, we first take the mass of fiber and then we pack it. Okay. And one thing is very important, a particular instrument is gauged, is calibrated, is for a particular type of fiber. Like an instrument which is meant for cotton, in that instrument, in that gauge, say fiber may be fiber diameter or may be fiber mass per unit length or directly may be micronaire value. In that instrument we cannot test other fiber, like for wool fiber diameter we can measure using air flow method, and it is gauged in directly in terms of micron. Okay. But if we use cotton in that instrument, we whatever micron we will get, that will be actual micron, because the density of fibers are different. So, that is why a particular instrument, particular air flow instrument is used for a particular fiber. Now, let us see with this animation here. Now, fibers are packed gradually. So, we are taking the fiber, we have taken the mass of fiber and gradually fibers are packed. This is a known mass of fiber of fixed, and for a particular instrument the mass is constant. So, that is the it is gauged, this is the direct reading of this flow is proportional to the mass per unit length. So, this is gauged either in terms of mass per unit length or in terms of diameter directly, and that is based on a specific mass of fiber. Okay. Now, the pump is we have started the pump, air is being sucked and the air is and the rate of flow of air is measured by this float. Okay. This float height is indicating the rate of flow, and this gauging is actually to measure the flow rate, but it is not gauged in terms of flow rate, it is in terms of directly diameter or micronaire value or mass per unit length. Okay. So, that is why here one thing is very important, suppose and the pressure, it is a we have to maintain this pressure. If the pressure is different, then we have to adjust the pump. Okay. So, to maintain certain pressure, for a constant pressure we have to measure the flow rate here. Okay. And now, one thing is important, the mass of a fiber. So, this is suppose for cotton fiber of a particular mass, say 4 gram or 5 gram mass, one in particular instrument is gauged for a particular mass of fiber. If we use suppose the 4 micronaire 4 gram of polyester is to be placed in the chamber. Suppose what will happen if we take say 5 gram or 6 grams of cotton, what will happen, the 5 if we take say 5 gram of cotton instead of 4 gram, this will result higher specific surface area, it will have higher surface area, and this float, the flow rate will be less and it will show as a finer fiber, the finer, but which is wrong. So, that is why it is very important to maintain the mass of fiber which we are packing, its exact mass of fiber. Okay. And also if we see, so we are maintaining the same mass, if we use say instead of cotton we are using say polypropylene. Polypropylene will have lower density, for same mass the fiber diameter will be say more and its surface specific surface area will be totally different and it will keep wrong result. So, it is very important that air flow instrument we have to maintain the mass carefully, we have to open the fiber. Another thing is that we have to open the fiber thoroughly. If we do not open the fiber, that means just let us see, suppose here we have not opened the fiber thoroughly. So, here suppose there is a cluster of fiber is there. What will happen? The air will not flow through this. So, this say there are 10 fibers are there, 10 fibers will be actually behaving like a single coarse fiber. So, that is why it is very important the openness of the mass should be totally uniform and the individual fibers should be open. It is a thorough opening is extremely important. Okay. And also as I have mentioned here, this pressure difference has to be perfect, it is a constant pressure difference, then we can measure the flow rate. Okay. And this the gauging, the gauge is actually, now let us see once again, this gauge, this is directly given the micronear value. So, for cotton it is given micronear value. How do we get this micronear value, this gauge? This is based on the large number of known micronear value, then only we can gauge. So, if we know the micronear value for a certain pressure, whatever, suppose it is a 4 5, so like it is a 4 micronear, then if it is known, that is called calibration of the machine. So, if we know the mass of the, and for a mass if we know the micronear and if it is 4, then we can say okay, this gauging is all right. Now, for a wide range of micronear we use the different types of fiber, different micronear, and we gauge accordingly. Okay. Now, so this is the air flow method. Now, we try to see if we change the micronear value here, this is for finer micronear and this one is for coarser value. Okay. This is for coarser fiber, we are packing it. This process is exactly same as earlier we have seen. Now, we are starting the process. Its pump is started. Now, air is flowing. And the float is showing the micronear value here. Okay. Now, this coarse fiber, now it is being replaced with the fine fiber. This is one particular fiber here. So, we are getting this value float. Okay. Now, this coarse fiber is replacing with the fine fiber. Now, it is fine fiber. Now, what happened? The flow rate is dropped. So, this is the change in flow rate. So, from there we can get idea about how the flow rate is changing. Okay. So, by measuring the rate of air flow under controlled condition, controlled condition means that this we have discussed, that is a proper opening, same amount of fiber. Okay. The specific surface area of fiber can be determined. So, we can actually gauge the fiber, it is as per the specific surface area also. Okay. And consequently, the fiber diameter we can measure, we can gauge in terms of fiber diameter or in terms of mass per unit length. So, fiber diameter is actually it is gauged for wool, and for cotton it is a mass per unit length, or it is a pre-calibrated for a particular fiber. So, that for a particular machine, as I have mentioned instrument, it is a pre-calibrated. So, two types of measurements are there. One is the measurement of air flow at a constant pressure drop, another is that measurement of pressure drop at a constant air flow. The two two ways of measurement is there. So, this is the method we have discussed. Now, next method is that optical fiber diameter analysis. This is very simple technique. It is a basically it is automated version of the projection microscope technique, as we have discussed, where the fibers are placed on a slide and it is manually moved in zigzag fashion and measure the fiber diameter. Here it is simply automated. The microscope stage moves in with the help of two computer controlled stepper motor. So, x y direction. So, it is a randomly it moves and we can program it. So, that way it moves and accordingly and the image is captured. Next is that so image is controlled with the video camera, it is captured with the video camera and digitized by frame grabber system. So, that is image processing we can get. Okay. The fiber diameter is then measured with the help of a pattern recognition software. So, that we can measure. Okay. The light scattering method, this is the it is called fiber diameter analysis. Okay. Analyzer, it works in a light scattering principle. This is not a microscopic technique, although light is used, it is a not microscopic technique, it is a non microscopic method of measuring the fiber diameter. It is by light scattering technique. Okay. Works on light scattering principle. The fiber cut into snippets with a very small length, typically 1.8 millimeter, that is a it is specified, and suspended in isopropanol, okay, to give slurry. So, this isopropanol is used because it is a non swelling chemical, okay, caused to intersect a circular beam of light in a plane which is at right angle to the direction of the beam. So, that means the light is actually projected on the slurry. The slurry it contains the fiber, small fiber, it is actually it is in the form of slurry, it moves through the a tube and the light is projected on that. Okay. And the beam light beam diameter is 200 micron. 200 micron of thin light beam diameter light beam is projected and the fibers are moving in a channel. Now, let us see the intensity of scattered light is proportional to the projected area of fiber. So, that means the fiber that is diameter, more diameter, higher the diameter, higher will be the intensity of light scattered. So, 200 millimeter, so most of the all the fibers are less than what we are measuring, the less than the 200 millimeter diameter, but what we are measuring the scattering of light, scattered light, quantity of scattered light. So, quantity of scattered light it is proportional to the diameter of fiber. So, higher scattering means higher diameter of fiber. And another arrangement here it is made, it is only fibers that completely cross the beam. there will be some fiber, few fibers which crosses the beam partially. So, the 200 millimeter diameter, 200 micron diameter beam, circular beam is moving. So, and the slurry is also moving. Okay. So, if the fiber is not crossing 100%, now let us see, suppose this is a beam of light cross section. Okay. Now, here there is a flow, okay, at right angle, fibers are moving with a slurry. Okay. There will be few fibers, suppose this is a beam, few fibers which are not crossing completely in this way, partially it is crossing. So, it is also scattering. So, that if it scattered, the partially actually that is projected fiber, if it scattered, so it will scatter the less quantity. So, that means this fiber is scattering, that means it will give a wrong result. It will show that as if the fiber is smaller in diameter. So, that fiber we have to discard, okay, that fiber, and only fibers which crosses completely, those fibers we have to take. Now, there is a technique that I will explain. So, the fibers, only fibers that completely crosses the beam are recorded, okay, so that the scattered light pulse is then proportional to the diameter of fiber, okay. And the flow rate is such, flow rate and concentration of the slurry is maintained in such a fashion that one fiber at a time is intersected. That means, if the flow rate is very high or the concentration of the slurry is very high, that means a number of fiber will cross the light beam at a time. So, it will give wrong result. So, the through the light beam one at a time. Okay. So, that means such that fibers intersect one at a time. So, that will give the correct result. These are the preconditions. Now, this is the arrangement here. Just see, this is the light beam of 200 millimeter. Now, here it is a, this is the fiber, here it is the sensor here, this one is the sensor and this is a splitter, this is a splitter, light is splitted in two equal part. So, here we know the actual intensity of the fiber, actual intensity of the light here, and the fibers are moving, this is with the slurry, okay, with the liquid flow, with the slurry, with the fiber, okay, snippet, it is moving in this direction, and the light beam, this is the in other direction, you can see this is the light beam, this is the light beam at the right angle. Now, fiber, as fibers are moving away from this, and this will be counted, this fiber when it is moving crossing this light beam, it gets, it refract, it actually scatter light, and that intensity of the light is recorded, okay, and it is compared with this, this is the reference value, the intensity of light is recorded and that is proportional to the diameter. Now, the technique here is that here there is a beam splitter, this is the actually split detector. Now, this split detector here, its function is that it will actually detect any fiber which is fully crossing or not, that it will detect. Okay. Now, you can see here, these are the fibers with the slurry, it is moving. Now, light beam is passing through. The same light, okay. Beam splitter, splitting it to two parts, and here it is a fiber snippet when it is coming. and if it crosses properly, fiber is crosses properly, then this is the split detector. Here it has got two parts, upper part and lower part. The intensity of these two parts should be exactly same, whether it is a low or high does not matter. The intensity should be exactly same, then only that particular data will be taken. Suppose the fiber is moving partially, then intensity will be different. Okay. Intensity of upper side, higher side or lower side will be different, or it will detect, okay, it will tell that this fiber has not crossed the beam properly. Okay. So, that is how this split detector will indicate. Okay. This is the principle of measurement of fiber diameter. The snippet which do not fully intersect the beam are rejected. Data from split detector. Split detector will tell that will automatically get rejected. So, unequal signals from the two detectors will be there. So, the results are detected. If the signals are same, then the particular result will be taken. Capable of measuring 50 fibers per second, it is a very high measuring technique, okay, high speed measuring technique. The beam diameter is maximum 200 millimeter. Can we have a larger beam diameter? We can definitely have. Why 200 millimeter? Because to actually accommodate that, so that to reject any crimp of the fiber, to reduce the effect of any curvature due to the crimp of the fiber. So, that is why we have to use the very fine diameter of the beam. Next method is the, it is a vibration method. Here we use the basic principle of vibration of rod, and this method is used for individual fiber, okay, one fiber at a time. Okay. In earlier methods we have seen it is a mass of fibers. Okay. Now, it is a, this is the only method where we use the single fiber for measuring the mass per unit length. Here we directly get the mass per unit length. An indirect method of estimating the mass per unit length by using the actually basic theory of string vibration. Okay. Now, this is the, this we know, this is the principle. So, frequency, that is the natural frequency, is equal to 1 by 2 L multiplied by under root T by M, okay, where T is the tension on the string, F is the frequency, L is the length of the free length here between the 2 points, and M is the mass per unit length. Okay. So, in this way, with using this formula we can measure the mass per unit length. So, the natural frequency, okay, tension and fineness, mass per unit length of the string are correlated as this formula, as we have seen. So, mass per unit length we can measure using this formula. If we know the tension in the string, length and the frequency, if we can measure the frequency, then we can, this is the natural frequency, okay, resonance frequency. F is the natural fundamental frequency of vibration, T is the tension in dyne, and frequency is the in hertz cycle per second, mass per unit length is in gram per centimeter. Okay. This is the gram per centimeter we can get, and L is free length in centimeter, and wavelength is that the lambda by 2. Okay. This is, so, you can convert it to in terms of wavelength also. So, the string is clamped, this string is clamped between two ends. So, one end and laid over the knife edge support. Okay. It is at this end it is clamped, and other end it is supported by a knife edge, okay, sharp knife edge, and known mass is hung, okay, loaded by W, and so the tension on the string will be Wg, okay, and is induced a natural vibration of frequency f. So, we can calculate, if we know the natural frequency of vibration, then we can calculate the mass per unit length. So, how to get the natural frequency? So, we have to vibrate this string with wide range of frequency, series of frequency, and in one particular frequency, intense frequency, it will have very high vibration. That is why that frequency is the natural frequency, and tension T equal to Wg is, it is a range between 0.3 to 0.5 centinewton per text. That is the tension we have to apply here, and we can convert this mass per unit length in terms of denier by simply multiplying by 9 multiplied by 10 to the power 5. This is the direct, we can measure the denier of the fiber. Fiber is then caused to vibrate either by vibrating top comb or by using transducer. Okay. So, we can allow the fiber to vibrate, and the amplitude of vibration is measured over a range of frequencies. We can actually vibrate at different frequency and amplitude we measure. So, the frequency where amplitude is maximum, that frequency is taken, okay, which gives the frequency which gives maximum vibrational amplitude is the fiber resonance frequency. That frequency is f, okay, that is taken for calculation, from which linear density is measured. Now, this is the technique. Here this is actually the vibrator is there, and here it is vibrated with a wide range of vibration, and where the maximum frequency is there, that value is taken. Now, actually there will be different fibers of different initial modulus, Young's modulus. This method is normally used for man-made fiber, and man-made fibers like polyester will have say different say length, same everything remains same, okay, but will have different say Young's modulus, and this Young's modulus, difference in Young's modulus will lead to different amount of frequency. So, if we change, if the keeping all other parameters constant, if even the for same diameter, same mass per unit length fiber, if the Young's modulus of two fibers are different, that will affect the frequency, fundamental natural frequency value. So, how to correct this? So, if our idea is to measure the mass per unit length, but if it changes with the Young modulus, then we will get wrong result. So, to counteract this value, so this is the modified refined formula it is used, considering the Young's modulus here. So, here if we use the Young's modulus, if we take the Young's modulus here and if you use it, then we will get the actual mass per corrected mass per unit area. It is a fineness of fiber. So, refinement of above equation to allow the stiffness of fiber. So, if the stiffness of fiber increases, so if it is high, then this value will also be high. So, that is why, so that is it's if it increases, so this value will also be it will be different. So, accordingly we can modify the equation, we can get the correct result. Okay. So, earlier equation was this one. So, this portion has been added, okay, for correcting with the different stiffness. Now, one simple example is that in a vibroscope, that is the instrument measure the work in the principle of vibration principle. In a vibroscope, the tension applied on the fiber sample is 150 dynes, okay. That is the tensile applied, and the free distance between the clamp and the support is 2 centimeter, that is the free distance. The natural fundamental frequency of vibration of the fiber sample with this setting is found to be 1 kilohertz. Calculate the fineness in decitex. So, this data has been directly actually given in such a fashion, then we can use the formula, the given formula directly. So, here tension applied is 150 dyne, free length of support is 2 centimeter, and natural fundamental frequency is 1 kilohertz, that means 1000 hertz, and fineness we have to measure. Now, this is the formula, it is a formula for denier as we have known. So, this Wg, it is nothing but the dyne, and this is the length. So, we can get this is dyne, lambda is a frequency is equal to 2 twice L. So, it is a 4 centimeter, and frequency f is the it is a 1 kilohertz, the 1000 hertz. So, we can simply replace this value, you can use this value 150 by 4 square, 150 by 4 square multiplied by 1000 square, the 9 multiplied by 10 to the power 5. So, if we get this value, it is coming out to be 8.4375 denier. This is in denier, and from denier to decitex, if we want to convert, it is a divided by 0.9. So, we are what we are getting? We are getting the decitex of the fiber is 9.375. So, this is the this way we can actually calculate the or decitex, we can measure the fineness of the fiber. Okay. So, we have discussed all the methods of measuring the fiber fineness. Okay. So, this is the decitex, and thank you.